Hello, everyone. So there is one case we haven't looked at yet with limits, which is what happens when as x tends to infinity or minus infinity, the value of the function is also going to infinity or minus infinity. So that's the one case we haven't done. So let's take care of it now. And it's going to be pretty much as you'd expect. So we're trying to let x go to infinity. So we have to assume that f is defined on some interval from a to infinity. So f is defined for all sufficiently large values of x. So it makes sense to approach infinity. And let's suppose we can make the value f of x arbitrarily large by making x sufficiently large. Okay, so why does this make sense? Remember, we have these two pieces that we put together depending on the case. So right now, we're trying to define what it means for the limit as x goes to infinity of f of x to be equal to infinity. So the output should be approaching infinity. So we want to make f of x arbitrarily large. And the control we have is that x is approaching infinity. So we should be able to make x sufficiently large. So remember the combinations and put them together. So if we can make f of x arbitrarily large by making x sufficiently large, then we say that f of x tends to infinity as x tends to infinity. And there is the notation you would expect. So the limit as x tends to infinity, f of x equals infinity, or f of x tends to infinity as x tends to infinity. Okay. And similarly, you can define the limit as x tends to infinity of f being minus infinity. So what would that say? Well, we want to make the values of f of x go to infinity. So we would say we can make the value of f of x arbitrarily large negative. And then the control we have is that x is going to infinity. So we would say provided x is made sufficiently large. So we can make the values of f of x arbitrarily large negative, provided x is made sufficiently big. And then we would do the same thing with the limit as x tends to minus infinity. We would say, okay, provided x is made sufficiently large negative. Okay, so many combinations, you can put them together, but they're all based on the same few building blocks. So remember the building blocks and how to put them together. So here are a couple of examples with infinite limits at infinity. So for instance, the graph of e to the x, the limit as x goes to infinity of e to the x to infinity. If we want to see what that looks like, remember back to the definition, we can make the value of our function arbitrarily large, provided x is sufficiently large. So whatever number I draw along the y-axis, however large I want my function to be, I can always make my graph lie above that value, provided I make x big enough, right? Whatever value I pick, I can make the function lie above that value, provided I just look far enough along to the right by the time, and so that the function has had time to grow. And okay, just for the record, as x goes to minus infinity, e to the x goes to 0. So that's a common mistake people make. So do remember, as x goes to minus infinity, e to the x goes to 0. Okay, here is y equals x cubed. So we see again, we're pretty much the same explanation as e to the x. As x goes to infinity, x cubed goes to infinity. Now the graph is slightly different as x goes to minus infinity. So x cubed tends to minus infinity as x tends to minus infinity. If we want to remember what that looks like from the definition, okay, it would say that we can make the value of our function arbitrarily large negative. So we can make it lie below any horizontal line, provided we make x sufficiently large negative. So I can make the graph lie below some particular number, provided I look far enough along to the left. And clearly that's the case here. So x cubed tends to infinity as x goes to infinity, and x cubed tends to minus infinity as x tends to minus infinity. And with other powers, it's pretty much what you'd expect. So remember, the graph of x cubed looks like this. The graph of basically all the odd powers, so x to the power of an odd function, looks similar to the graph of x cubed, except it's just steeper on each side. What about even? Well, for instance, if you had x squared, then it would be going back up again on the left, right? It would look like the graph of x squared. So then we would have, and similarly for all the even powers, it would look like that. Okay, so all of them are going to infinity as x goes to infinity, but when x goes to minus infinity, we have to care whether the power of n is odd or even. So if it's odd, like with x cubed, then x to the n goes to minus infinity. If it's even, like with x squared, then it tends to infinity. Okay, and we've seen a couple of different types of functions that all grow to infinity as x goes to infinity. But not all growth is the same, right? Sometimes speeds of convergence of different functions or speeds of which things are tending to infinity are different. So as a kind of general rule of thumb that can be good to keep in mind is that exponentials like e to the x or 3 to the x, 4 to the x, 10 to the x, where the x is in the power, those things grow very quickly indeed. If you try to make some computations, you'll quickly bamboozle your calculator. And then next we have polynomials that are kind of a medium rate, so x squared, x cubed, and so on, where the x is in the base and then the power is a number, it's just a constant number. Those are reasonably fast, and the higher the power, the faster the function grows, right? X to the 2020 is going to grow way faster than x squared. But whatever the power, eventually it's not going to be as fast as e to the x. Exponentials are the fastest. Okay, and then lastly, logarithm. So natural logarithm of x still goes to infinity, but it goes to infinity very, very, very slowly. So that goes to infinity, but slow. And why is this useful? Well, later we're going to have more rules for finding limits, but just for the moment, it's useful to keep in mind that the higher order, if you have a higher order function divided by a lower order function, then it's going to go to infinity. Or if you have a higher order function on the bottom, then it will go to 0. Okay, and if you have the same kind of order on the top and bottom, then you have to do something else, say with algebra. But for instance, here, if we look at e to the x divided by x cubed plus ln x, then in my kind of rule of thumb, e to the x is growing very quickly. X cubed plus ln x is a medium plus a slow. It's kind of medium rate going to infinity. So this is going to go to, this whole fraction is going to go to infinity. But this isn't a hard and fast rule, so I wouldn't lead with this. But if you're stuck and it looks like you have things going to infinity and you're not sure what's going on, this is a good idea to get it's a good rule of thumb to get a direction of where you're going or what you're looking to try to do. And we'll see more tools later, like L'Hopital's rule. Okay, thanks everyone. See you next time.